How stars work. In order to have a stable star, the energy it emits must be the same as it can produce. There must be an equilibrium.
The main source of energy of a star is nuclear fusion, especially the proton-proton chain, which can transform hydrogen into helium.
The energy generated in the core is transported outside by two main mechanisms, radiation and convection. The radiation process consists just of photons emitted by the sun, and the convection means huge movements of material all throughout its interior, as you can see on the cover. Scientists call this balance hydrostatic equilibrium.
There are two main forces acting in a star.
Gravitational contraction. It is due to the higher layers. This force pushes mass to the center.
Radiation pressure. It is produced by the inner layers, and it forces material upwards.
The different layers of the sun. The sun, like other stars, is a huge spherical object made of hydrogen and helium.
Its diameter reaches 1.4000 kilometers, or 109 times the Earth's diameter, but is 4 times less dense than the Earth due to its composition.
The sun is not only made of the glowing gas that we see with a telescope. It has, exactly like the Earth, different layers at different temperatures. Every layer has its own features which makes them interesting.
Below is a figure of the structure of the sun with all the different layers and components named.
The core. The core of the sun is the source of all its energy.
The amount of energy produced is nearly continuous, so we do not see a considerable variation in its brightness nor the heat that is given off. The core has a very high temperature, and the material it is composed of is very dense due to the extremely high pressure. It is the combination of these two properties that creates an environment where nuclear reactions can take place. These nuclear reactions always produce heavier elements on the periodic table.
The radiative zone.
The transport of energy from the sun's core where it is produced to the regions that surround it can be done by transferring it by radiation.
This is how it travels from the center of the sun to the outer regions, hence the name radiative zone. Through this area of the solar interior, the energy in the form of radiation is transmitted by its interaction with the particles in the surrounding.
Some atoms are able to remain intact in the radiation zone, since the temperature is slightly cooler than what it is in the core. These particles are capable to absorb energy, stock it for a short time, and then later release that energy as new radiation.
In this way, the generated energy in the core is passed from one atom to another, wandering on an upwards path through the radiation zone.
The convection zone. The energy that is initially created in the core needs a new transport mechanism to carry on its passage to the sun's surface once it is out of the radiation zone.
This is necessary since the temperature is relatively cool outside of the radiation zone, 2 million degrees Kelvin, compared to 5 million in the radiation zone. Atoms will absorb energy much more easily at this temperature, but they do not release it so readily since their surrounding is cool and dense.
Therefore, the energy transfer by radiation slows down considerably. The atoms are heated up by absorbing the and rise through the convection zone, bringing this energy heat towards the surface.
The photosphere. The photosphere is also named the apparent surface of the sun. Since the sun is wholly made of gas, there is no solid surface like there is on Earth. However, when we observe the sun, there is a depth past which the density of the gas becomes so high that we cannot see through it.
This region is called the photosphere, or as mentioned, the apparent surface.
This is the disk that one sees in the sky when one looks at the sun through a telescope that has a filter, or as a projection on, for example, a sheet of paper.
The chromosphere. The chromosphere is the layer above the photosphere and is thicker than it, with a very low density. It is impossible to observe it without narrowband filters or during a total solar eclipse due to the brightness of the photosphere behind it.
Furthermore, it's less dense than the photosphere. The corona.
It is the biggest and least dense structure of the sun, and it surrounds it,
composed of plasma escaping
from the sun that reaches 1 million Kelvin,
but with a density even lower than the chromosphere. Furthermore, the solar wind transports the material of the corona out to the interplanetary medium. From Earth, the corona is only visible during a total solar eclipse, and neither their temperature nor their composition are the same, so the solar activity on these layers is very different.
These different features are the sunspots. When looking at the sun through an adapted telescope or by projection, dark spots can sometimes be observed. These dark, continuously changing areas are called sunspots, and they are generated on the photosphere. They appear darker to the eye for the reason that their temperature is not as high as the neighboring gas.
This happens because the temperature of the sunspots vary from
3000 to 4500 Kelvin.